Good day, sir. Good day, everyone. This presentation is presented to you by the group EGG, Espinosa, Gamgam, and Gabalonsos Group. Objectives. Main topic, methods of controlling power. Subtopics, introduction to power electronics. How do power electronics work? Power components, topology, and control theory. The first is the introduction to power electronics. Power electronics is the branch of electrical engineering that deals with the processing of high voltages and currents to deliver power that supports a variety of needs, from household electronics to equipment in space applications. These areas all need stable and reliable electric power with the desired specifications. Power supply in one form is processed using power semiconductor, switches and control mechanisms to another form, supplying a regulated and controlled power. How do electronics power work? Power electronic systems are used in a variety of applications such as power generation, power transmission, power distribution, and power control. In all these applications, the input voltages and currents are switched using power semiconductor devices to provide desired outputs. The constructions of basic semiconductor devices such as diodes, FETs, and bipolar junction transistors or the BJTs are altered to withstand high voltages and currents. As a result, we have silicon-controlled thyristors or the SCRs, power diodes, power metal oxide semiconductor field effect transistors or the MOSFETs, power BJTs, insulated gate power bipolar transistors or IGBTs, gate turn-off thyristors or the GTOs, and so on. Power components. All power system components are liable to faults involving anomalous current flow and insulation breakdown between conductors or between conductors and earth. The insulation material may vary from air, in the case of transmission line, to oil, SF6, or a vacuum, in the case of switchgear. The transmission and distribution engineer is concerned with symmetrical faults involving all three phases, with or without earth, and asymmetrical faults involving phase-to-phase and one or two phase-to-earth faults. In addition, interturn winding faults also occur in transformers and electrical machines. The most basic power system components are generators, transformers, transmission lines, buses, and loads. So what is a generator? A generator, a machine that converts one form of energy into one another, especially mechanical energy into electrical energy, as a dynamo, or electrical energy into sound, as an acoustic generator. Transformer, an electric device consisting essentially of two or more windings wound on the same core, which by electromagnetic induction transforms electric energy from one set of one or more circuits to another set of one or more circuits such that the frequency of the energy remains unchanged, while the voltage and current usually change. What is a transmission line? So a transmission line is a system of conductors that transfers electrical signals from one place to another. The rising and falling of the waves moves the buoy-like structure, creating mechanical energy which is converted into electricity and transmitted to shore over a submerged transmission line. Buses is a network topology or circuit arrangement in which all devices are attached to a line directly and all signals pass through each of the devices. Each device has a unique identity and can recognize those signals intended for it. An electrical load is an electrical component or portion of a circuit that consumes or the active electric power, such as electric appliances and lights inside the home. The term may also refer to the power consumed by a circuit. This is opposed to a power source, such as the battery or generator, which produces power. Types of power electronic circuits. AC to DC converters, DC to DC converters, DC to AC converters or the commonly known as inverters, AC to AC converters or the commonly known as cycloconverters. So what is AC to DC converters? The input AC voltage is converted to DC voltage at required levels. A diode bridge rectifier is traditionally used for these applications, but this configuration results in currents that have high peak values and high harmonic content. Boost converters are commonly used to draw currents that are in phase with the AC voltage. DC to DC converters. The DC power input, whether unregulated or regulated, is converted to regulated DC power at the output. Without power electronic converters, it is very difficult to generate variable DC power. With the availability of different configurations of DC to DC converters, DC power at desired levels has become indispensable. Buck, boost, and buck boost converters are three basic converters that can step down, step up, and provide both levels respectively. So what is a DC to AC converters or the commonly known as inverters? So inverters are the input DC power from batteries is inverted to provide AC power. This AC power is used to control AC motors with precision and efficiency. A combination of AC to DC and DC to AC converters are used in high power transmission where two different grids are connected without worrying about synchronization. AC to AC converters or also known as the cycloconverters. The AC input that has a variable magnitude and frequency is processed to provide an AC output that has both regulated magnitude and frequency. Wind power generation is a popular application of these types of converters. The output of the wind generator varies in both magnitude and frequency depending on the wind speed. To connect this power to the grid or a load, the voltage and frequency need regulation. So the benefits of power electronics. Electric power is scarce. It is not prime importance to deliver the power to the loads with the minimum losses. Advancements in power semiconductor research has resulted in more efficient chemistries such as silicon carbide and gallium nitride. The benefits of power electronics are: first, high power density power supplies, improved efficiency up to 99% in power conversion. Noise-sensitive applications such as in medical devices are also transitioning to switching power supplies because of the efficiency and reliability. Power can be made available in desired form and level as per specifications. Increased clean power generation using power electronic interfaces to connect the sources to grid. And lastly, wireless power transfer. So the next topic will be presented by James Gamgam.
Topologies. Power supply topologies. The three basic topologies used in switching power supplies are buck, also known as forward, boost, and buck boost, also known as flyback. All three topologies use the same three elements: transistors, inductor, and diode, but they are arranged in different manners. Buck. The buck topology, shown in Figure 1, can operate in two states: continuous, where the inductor current never falls to zero, and discontinuous, when the inductor current falls to zero at the end of each cycle. The main advantage of buck converter is its simplicity and flexibility. The buck converter is typically used in supplies from 10 to 250 watts. A disadvantage is that the voltage stress across the primary switching element is 2 times the input voltage. This can be reduced by a variation on circuit whereby a second switch on the other side of the transformer winding is employed. The next one is boost. The boost topology, shown in Figure 3, is an indirect converter since the energy is only transferred to the load during the off time and switching element. It can operate in two states: continuous, where the current never falls to zero, and discontinuous, where the inductor current falls to zero at the end of each cycle. The main advantage of boost converters that it can increase the voltage and reduce the number of cells. Two battery-powered applications that use boost converters are used in hybrid electric vehicles or HEV and lighting systems. The last one is flyback. The flyback topology, shown in Figure 4, is an indirect converter since the energy is only transferred to the load during the off time of the switching element. It can operate in two states: continuous, where the inductor current never falls to zero, and discontinuous, where the inductor current falls to zero at the end of each cycle. Its advantages is that the primary is isolated from the output, capable of supplying multiple output voltages, all isolated from the primary. Ability to regulate the multiple output voltages with a single control. The flyback converters use very few components compared to the other types of SMPS. Control theory. In control theory, power electronics can be defined as the use of electronic devices to control and convert electric power. Therefore, every applications of power electronics involves some aspect of control, since the mathematical tools used to solve one control problem are often common to other problems. Some researchers specialize in formulating control algorithms for a variety of power electronics applications. Therefore, it is useful to review the major areas of power electronics from the control perspective in order to understand the broad-based connection between modern control theory and power electronics as a whole. Applications: static power conversion and control, static power supplies, motion control, heating and lighting. Static power control conversion and control. One fundamental characteristic of power electronic circuits is the discrete switching between two or more different circuits configuration. This is generally referred to as switch mode conversion. At the heart of the power electronic converter is the switch controller. Since the ideal output of a converter is usually either pure DC or a pure sinusoid, one of the primary concerns of switch control strategies is to reduce, or at least choose, the higher harmonics which are created by the switching. The next one is static power supplies. Power supplies, including uninterruptible power supplies or UPS, for computers, copiers, and fax machines, as well as huge HVDC systems and VAR compensators, depend on power electronics. Their efficiency and harmonic quality is largely a function of the controller. To reduce a hardware expense, the small DC power supplies usually incorporate simple control algorithms. But as harmonic standards are tightened, manufacturers will be forced to use more complex switch control techniques to improve the harmonic distortion on both the supply side and the load side of the converter. Motion control. The power electronic motor drives are used in virtually all newly installed motion control applications, such as industrial machine tools, conveyors, cranes, and hoists, electric vehicles, elevators, forklifts, and trains. Therefore, a natural extension of power electronics in this area is the development of motion control algorithms which provide improved control response, improved efficiency, and reduce hardware requirements. Additionally, the power electronic converters used in the motor drive are themselves power electronic converters with the same issues of reliability, efficiency, and harmonic quality as described above. Next is heating and lighting. Electric heaters, ballasts, and light dimmers in industry and homes consume a large percentage of nation's generated electricity. Power electronics can often achieve these tasks more efficiently and more effectively than the traditional devices. Because of the switch mode nature of power electronic circuits, the efficiency and harmonic quality of these devices depends heavily on the control strategies employed. Methods of controlling power. Power control systems means systems or devices which electronically limit or control steady-state currents to a programmable limit to improve process performance and save energy cost with our formidable range of power products, covering all types of load and voltages. These reliable products offer features such as high performance alarm strategies and advanced diagnostic load fault detection and supported by our vast experience in all types of power control applications. Power control methods. Number one is switch control. Number two is rheostat control, voltage control, and lastly, thyristor power control. Switch control. Switch control uses an electrical switch is any device used to interrupt the flow of electrons in a circuit. Switches are essentially binary devices. They are either completely on or closed or completely off or open. AC to DC conversion method. Shown here is the switching circuit configuration of a typical to AC to DC converter. The figure shows that the transition of the voltage waveform using the switching method. Unlike the transformer method, which first performs step-down AC to AC in the transformer block, with the switching method, the AC voltage is first rectified as is by the diode bridge circuit. High DC voltage is chopped or separated by turning on and off the switching element, then transmitted to the secondary side via step-down operation using high-frequency transformer. At this time, the chopped waveform becomes a square wave. Output waveform process. On the secondary side, the step-down square wave is half-wave rectified using a rectifier diode, then smoothed with a capacitor before finally being output as a DC voltage. Example of a switch. A switch is an electrical device, usually electromechanical, used to control continuity between 2 points. Hand switches are actuated by human touch. Limit switches are actuated by a machine motion. Process switches are actuated by the changes in some physical process, like temperature, level, flow, and etc. Simmerstat control method, one variation of switch control. A simmerstat is a switch that is cycled on and off by a small heating element inside it. The actual switch contact is mounted in a bimetal strip that bends as its temperature changes, opening and closing the switch. The next topic will be discussed by Ralph Gian Gabalonso.
Rheostat control. So what is a rheostat control? Rheostat control uses a series-connected rheostat or a variable resistance to control load power. As resistance is introduced in series with the load voltage and hence AC power is reduced. The reduction in load voltage is caused by the voltage drop across the rheostat. AC power may be controlled from a very low value up to full power. However, for a wide range of control, the rheostat may be physically very large. It may in fact be larger than the load. To control the load, power must be dissipated in the rheostat. This is a power loss and results in poor efficiency at low load settings. When the load power is reduced to 50%, the power dissipated in the rheostat is equal to the load power. This form of control is widely used in equipment of old design. Owing to its low efficiency and generally poor performance, it has now been largely suppressed by more modern methods. So this is the example of the rheostat presented in the screen. A rheostat is an electrical instrument used to vary resistance that usually consists of a coil of wire with a terminal at one end and a sliding contact that moves along the coil to stop the current. Next is the voltage control. What is a voltage control? Voltage control method controls the load power in the same manner as rheostat control, that is, by varying the load voltage, but uses either a variac or a tap inductor. These methods are suited only to AC supplies and loads. The use of the variac or the tap inductor overcomes the poor efficiency of the rheostat method. So this is the example of the variac and inductor. Next is variacs and inductors are very efficient devices compared with rheostats. A variac is a form of transformer. It is a variable autotransformer. These devices are efficient, but they have the disadvantage that they are bulky, heavy, and expensive, particularly where the load power is high. Voltage regulator. So what is a voltage regulator? Any electrical or electronic device that maintains the voltage of a power source within acceptable limits. The voltage regulator is needed to keep voltages within the prescribed range that can be tolerated by the electrical equipment using that voltage. Next is the thyristor power control. So what is a thyristor power control? Thyristor power controllers or SCR power controllers control power or voltage applied to a load. Typically, applications are generally found where power needs to be varied and ultimately converted into thermal energy. So this is the example of the thyristor power control. Thyristor controllers achieve efficient AC power control methods. Number 1, phase control. Number 2 is zero voltage switching. Number 1, what is a phase control? Whenever we talk of phase angle, we generally mean the angle of a sinusoidal quantity at any instant of time. Phase control of SCR means the phase angle with references to source voltage, where it is getting turned on by the application of gate signal. What is a phase-controlled thyristor? The AC waveform is chopped up to achieve varying values of a load voltage. The load voltage waveforms are no longer sinusoidal, but many applications this is not a problem. The variable voltage is obtained by delaying the triggering of the thyristor and hence reducing the conduction time. Number 2, zero voltage switching. Zero voltage switching or ZVS means that the power to the load, heater or cooler or other device is switched on or off and only when the output voltage is 0 volts. Load waveforms from zero voltage switching. So these are the different kinds of waveforms from zero voltage switching. High power, medium power, and low power. In zero voltage switching, the methods of control device is to overcome the RFI generated by phase control techniques. It operates in a similar manner to a thermostat in that the load voltage is controlled by controlling relative on or off times. In this case, however, the on and off times will be measured in cycles. And that's all. Thank you, and we hope you learned something.
That's all.